Thank you very much
Thank
for
you.
the introduction, and many thanks for the organizers as well. I really enjoyed the conference. So today I'm going to talk about mechanical artifacts in tomography. Tomography is a very powerful technique. It has many applications in many fields, including biomedical imaging, material science, as well, and so on. So in my work, we focus on mechanical artifacts in tomography, because sometimes in the reconstruction images, you can see different type of artifacts, in particular due to these mechanical errors in the imaging system. So what we want to do is to help the experimentalists to identify the cause of these artifacts and help them model the system and eventually design computational tools to remove these artifacts. So tomography, it allows us to see through the sample without cutting it open. A common example that you may know well is the X-ray computed tomography. So X-ray beams transmit through the human body. The intensity of the beams is attenuated and then recorded on the detectors. As we rotate the X-ray source, you can see here in this small animation, a 2D sinogram is generated. Then we apply some inversion algorithms to recover the 3D volumes that we are interested in. So the modality I'm going to talk about today is an optical analog to X-ray CT. It's called optical projection tomography. And OPT. OPT, similar to X-ray CT, it can work in a transmission mode where we use diffuse white light. But additionally, OPT can also work in the emission mode, which means we can use some wide field excitation light to illuminate a fluorescent sample. Then we collect the emitted photons. OPT is typically used to image small animals such as a liver fish or small embryos of mice. Also large organs of small animals such as lungs or intestines. And the imaging ability of OPT is typically up to a few cubic centimeters and at a resolution of about 30 microns. So the general setup of OPT is very similar to X-ray CT. We have a sample that is rotating and we have a camera that's detecting the projections. Big difference is that we have a lens system to focus the light on the sample. And typically this lens system has a low numerical aperture. And while you may wonder how come this even works, because light is strongly scattered by biological tissues. So how does the light even reach the detector plane? In OPT, we optically clear the sample, which means it's basically transparent. So we reduce the scattering and any kind of refraction as well. So that in this setup, the light rays will approximately pass through the sample in straight rays. This means that the mathematical principle of OPT is basically the same as X-ray CT. It's a strict ray projection. And now let's have a closer look at the mathematical principle. Typically, the information contained in one horizontal slice of the sample that is perpendicular to the rotation axis is recorded in one horizontal row of pixels on the detector plane. As the sample rotates, this line of pixels will record a 2D sinogram. And this mathematically, this process is called the 2D Radon transform. And to reconstruct the image, we can either use the inverse filtered back projection algorithm or some iterative reconstruction methods. Then we obtain a stack of 2D slices. While this whole pipeline works very nice, there's a common issue in the OPT reconstructions, the artifacts. And the artifacts can happen due to different reasons. They can be instrumental reasons. For instance, if we have some fluctuation in the light source or some pixel variations in the detector response, we see these smear and ring artifacts. And artifacts can also happen due to optical reasons. For instance, due to the limited depth of focus, we have these arms and legs that appear around a point, what is supposed to be a point in the reconstruction. Artifacts can also happen due to, for instance, refractive index mismatch, if you noticed my poster yesterday. And today we're going to focus on the last category. It's called the mechanical artifacts in the system. For instance, the sample may move or be shifted during the experiment. So artifacts, when we look at them, we try to approach them from three aspects. What do they look like? And what causes these artifacts? And how do we correct them? So following this approach, we're going to take a look at the most common type of artifacts in OPT, the shift of the sample. So in the ideal case, the sample is aligned with the rotation axis, and it's rotating around the rotation axis. But in practice, typically we have a small shift of the sample so that it's off center with a few microns. Then the sample is rotating kind of in a circle. And the resulting artifacts come in different shapes. For point-like objects, we see these circles. And for continuous structures, we see these kind of double edges or shadows. In both cases, the larger the shift, the more severe the artifacts are. And how do we correct this type of artifacts? There already exists a few techniques in the literature, such as max variance, center of mass. All these techniques, they rely on features either in the reconstructed image or features in the projection image. For instance, the max variance method relies on features in the reconstruction image, and feature point tracking relies on information in the projection image to estimate the shift. Another example of mechanical artifacts is a tiny tilt of the rotation axis. Tiny tilt, it can be approximated by a location-dependent shift. And let's have a look how it works. In this non-calibrated image, we see these shadows around the object. And typically, this is what people do to remove it. So we apply a shift correction method, the max variance method, on the top slice of the sample, then to find the center of rotation. Then we apply it again on the bottom slice, then fit the line. And now we have determined the center of rotations for each slice. Then we have a calibrated reconstruction image without artifacts. So for now, we have looked at these existing studies on mechanical artifacts. Either it's tiny tilt or it's a shift of the sample. They are all 2D correction methods, and they only focus on one type of error. So naturally, we want to ask ourselves if we can characterize all these different types of artifacts and then eventually design an algorithm to correct all of them. At the best case, all at once. That's exactly the motivation of our work. We want to find a 3D model to describe different types of artifacts in the system. Then we study all these different types of artifacts in a systematic way. And eventually we want to design one algorithm to remove all the artifacts. And before we jump into details, here's a quick overview of our contributions. So we first have a model of the imaging geometry of OPT in 3D. Then we use this model to classify different types of artifacts due to mechanical errors in the system. Then we propose a multi-scale auto-calibration algorithm to remove all the artifacts. So now let's have a look at the imaging geometry of OPT in 3D. We have light coming from the left side, propagating through the optical axis, y-axis, and arriving at the detector plane, the C camera. The sample here is represented by a cylinder that is placed in a 3D coordinate system X, Y, Z with origin O. And the detector plane is described by a 2D coordinate system C and eta with origin O prime. The sample is first shifted to any location G. And we describe this shift of the sample by this coordinate. The sample can also be tilted in any orientation. And we decompose this tilt into two components. The first one is a tilt of the into the camera. We call it out of plane tilt. And the second one is a tilt that is parallel to the camera, which described this by angle psi2, which represents the rotation of the camera. And in the end, we have the sample rotating around its own orientation axis at the different angles, typically over 0 and 360 degrees. And we represent these by a vector phi. So now we have basically in total 6 geometric parameters that completely describe the 3D imaging geometry. We have seen shift in the x direction because circles and double edges. And to quickly mention it, if you have a shift in the y-axis direction, you will have an autofocus blur. And if there's a shift in z, there's no artifacts. So now we focus on tilt, 3D tilt, because it has not been seen in the literature yet. So to characterize 3D tilt, we used we simulated some point-like objects, beads, to characterize the system. Our volume is a stack of slices of 512 slices, and we choose the 3 representative slices to show you the reconstruction results and compare to observe artifacts. In both cases of two tilt angles, psi1 and psi2, we see that the artifacts, they have dependence on the field of view, location in the field of view. So the further away you go from the center of the image, the more artifacts you observe. The artifacts also have a dependence on that location. So the further away we go from the center of the image, the more artifacts we will see. And obviously, it also has a dependence on the tilt angle. The more we tilt, the more artifacts we see. And when we compare parallel with psi1 and psi2, we see that under the same conditions, psi2 causes more artifacts than psi1. And furthermore, psi2 has a stronger dependence on that location compared to psi1. And to some, the 3D tilt artifacts has a dependence on the location in the field of view, on location on the z-axis, and also the rotation angle, the tilt angle. And they come in various shapes, which means the 3D tilt is a very complex problem. This motivates us to try to model it in 3D more precisely. And the last type of mechanical artifacts that can happen is the inaccurate rotation angles during acquisition. And this can happen when we process or we have a low-cost system. And then sometimes a random error will accumulate in the rotation angles. This will eventually result in a mismatch between the actual angles that we use, the actual angles and angles we use in a reconstruction. So you can see this results in this kind of wing artifacts. They have a dependence on the location in the field of view. And depending on if the error is positive or negative, they have a direction. So either they're flying towards the center or away from the center. Now we have seen all different types of artifacts. We put them in this table. So people have already studied the translation or shifts in different directions, and they cause different type of artifacts, and they usually don't depend on the field of view or Z location. And in 3D tilt in addition, and we decompose them into 2 parts, the psi1 and psi2, and they cause different types of artifacts, and they have a dependence on the field of view and also on the Z location. In the end, we also see artifacts in the due to rotation angle errors, and because it's wings or seagull artifacts. So now the question is, how do we correct these artifacts? Here we propose a multi-scale auto-calibration algorithm, and this part I will divide into 3 subparts. We first will take a look at the forward image model that we adopt for the OPT. And then we take a look at the inverse problems that we're going to be solving. It involves parameter estimation and as well as volume reconstruction. And then in the end, I introduce the calibration algorithm. I will talk about some practical challenges we have with our experimental data sets, and then tell you how the multi-scale scheme works. So first, the imaging model we use for OPT is the 3D X-ray transform. It describes three discrete projections of 3D samples. So the formula says the intensity, the intensity at the location B on the camera plane is equal to the X-ray transform project operator applied on the unknown volume F with parameter of rotation angles theta and essentially a shift T plus some detector noise. And this model is valid under two assumptions. So we omit the optical effects in the system, and our system has a low numerical aperture. So to numerically implement the forward model, we discretize it. The most common way to discretize forward model is to adopt just a rectangular basis. Then we represent F by a vector. But this is not the most ideal case, because in this discretization, it's not differentiable with respect to the parameters that we want to estimate, beta and t. So we cannot use gradient methods. To do better than this, we use instead another basis function called the optimized Kessler-Bessel windowing function. Unfortunately, under this discretization, we can represent the volume with a series of coefficients and this coefficient vector C. And this time it's differentiable, and we can leverage gradient descent-based methods. And even better, it's proven that there is an analytical expression of the gradient. So now we formulate our inverse problem as the following optimization problem. So C is the volume that we want to reconstruct, and the theta and T are system parameters that we want to estimate. And the cost function now is defined in the least square fitting fashion. So we want to solve this problem in a joint fashion. We want to reconstruct the volume and at the same time estimating the system parameters. For the reconstruction part, we use VISTA, the fast iterative shrinkage threshold algorithm. And for the calibration part, we use a semi-coordinate wise gradient descent method. And this is how it works. So we start from an initial gas, usually zero gas for the volume. So we have an empty volume, and then a set of parameters that corresponds to a perfect system free of errors. Then we run one step of reconstruction to get a rough estimate of the volume. Then we run one step of calibration to update the parameters. Then we do this again, and so on, until we have a very good estimation of the system parameters that we can use to do 3D reconstruction free of mechanical errors. Now this pipeline looks good. There are some challenges we need to address with our experimental data set. The first issue is the computational bottleneck. The size of the OPT projection data set is typically over 10 gigabytes. And unfortunately, it turned out it's infeasible for the computational power we have at hand. On CPU, it is too slow. And when we try to accelerate it on GPU, we don't have enough memory. So to solve this problem on top of our heads, we downsample the measurements to a smaller scale so that it's feasible for our machine and also not too slow. Then when the calibration is done on this coarse scale, and afterwards, we go to a final scale to do the final reconstruction. The second challenge is the initial gas for some system parameters. This is because the calibration of the system parameters, it's a non-convex optimization problem, which means when we try to do gradient descent on this problem, it feels like hiking somewhere in the Swiss mountains full of valleys and hills. When we start from different points and follow the local slope, we end up at very different locations, while the global minimum could be somewhere here. This means that it is very important to choose the starting point. So to get a good initial gas is very important for us. So how do we achieve that? We found out that For the angles, when we use this zero gas, it works fine. The algorithm is okay. But when we use zero gas for the shifts, it doesn't work anymore, which means we need to have some pre-estimation of the shifts. So after trying deeper methods, we found out that following heuristic method is fast and the most effective. So it's very similar to the max variance method. We just start from a range of gases, and then we apply these shifts in the projection image. Then we just reconstruct and observe the cross-section of the image until we see that at some values with the reconstruction quality is better. Then we just choose this value as a rough guess for the shifts. Now we have all the pieces together. Here's an overview of our multiscale calibration and the reconstruction algorithm. So we start from initial gases for this system parameters. Then we downsample our measurements. Then we run our calibration on this coarse scale. It's basically composed of alternating between reconstruction and calibration. And when it's well calibrated, these parameters, we use them to do a final reconstruction at a higher scale. So we first validated our algorithm on some simulated data. We simulated some ground truth with speeds, and we artificially added error in the rotation angles and also the shift. Then we apply the forward model on the ground truth to simulate measurements. Then we apply different reconstruction methods to and compare the results. So when we apply direct FBP, as expected, we see these circles that are due to the shift and these wings that are due to the rotation angle errors. When we first do a shift correction using the method I mentioned before, we see the circle goes away, but we still have some other artifacts, the wings. And when we apply our calibration algorithm, then do reconstruction, we see we manage to remove all the artifacts. We also validated our algorithm on experimental data sets of fluorescent fibers. So what we did is we want to calibrate the 3D tilt. So we experimentally added error by tilting the rotation stage to different directions, psi 1 and psi 2. Then we acquire these projections. We tried our calibration on 4 different cases of in-plane tilt angles. And in all the cases, we start from a zero gas, so we don't have any information about the tilt angle. And then it turns out calibration managed to find a value that is very close to the true angles. Here's a reconstruction image of in the case of a 4 degrade tilt angle. When we apply direct FBP, we see many ghost shadows. And when we do a shift correction, we already mitigate some of the artifacts, but we still see it's not perfect. Then we apply our calibration, we manage to remove these artifacts. We also further compared the value of the cost functional to have insight into our algorithm. So if we only run iterative reconstruction for many rounds, for instance, 180 iterations, we only manage to bring down the normalized cost to 0.4. But if we put in some few steps of calibration in between, for instance, every 30 iteration, we put in a calibration step, we see this jump down of cost. And this means that calibration, it indeed reduced the model mismatch, which is the origin or the root of why we have these mechanical artifacts in our reconstruction image. And to sum, we talked about imaging modality called optical projection tomography. It's an optical analog to X-ray CT. The OPT reconstruction images sometimes suffer from artifacts, in particular due to mechanical errors in the imaging system. We used a simple forward model to describe the 3D geometry of OPT. Then we use this model to classify the different types of artifacts according to their appearance, their cause, and the correction methods. This provides a guidance for experimentalists to have an insight into the system. And in the end, we propose a multi-scale auto-calibration algorithm to remove the artifacts. I would like to thank my co-authors from my group and also from IDEA for the joint efforts on modeling, computation, and data acquisition. Thank you very much for your attention. I'm happy to take any questions that you may have.
Thank you. So,
hi, thank you. Very interesting work. So essentially, you're doing a joint reconstruction and optimization of your 6-parameter model, right?
Yes.
So is this model exhaustive, or do you think there's better models? Because you could also say, like, you know, essentially it's a post-estimation problem, yes, for each of these views that you are having. You could also say, like, you know, I use 6 parameters per view, which is a rotation and a translation under which I'm seeing the object, and I just do the same kind of optimization. Now it will be more flexible, and because I don't need to assume a common tilt axis or like whatever, it will sort of wiggle its way, more like bundle adjustment in computer vision, basically. Do you think you could further reduce the error with that? Or so do you think there's still a model mismatch between your 6-parameter model and what's happening in reality? I mean, I think that's underlying the question.
I agree with you. There's if you try to let's say make a post estimation, such as in cryo-electron microscopy, you do have more freedom. But in the specific setting of a setup of OPT, we know how it works. We do have a fixed rotation axis, so that we don't need so many degrees of freedom in terms of rotation, for instance. So in terms of if this set of geometric parameters is sufficient, I would say it's probably sufficient for this specific setting.
Yeah, but you still have this your normalized error doesn't go to 0, or
yes,
not close to 0, right?
Yes,
so
that's true. But because we use the model that is simplified, I would say also a large amount of work in OPT is devoted to model the light path, because we here use a straight ray projection like X-ray CT, but in reality the light is it has a point spread function that is not a direct delta, so it's like this, like a Gaussian beam, something like that. With this we didn't model, and also there are other type of artifacts that we didn't consider in our model, so there will always be a residual model mismatch. That's why the images don't look so perfect in the end.
Are you following the computer vision work? Because these people will tell you these days, you know, oh, you just put a nerve and bundle adjust on top of that, like everything's differentiable anyway. You don't need to do any manual modeling, so to say. Yes.
Sorry, I didn't get.
We can talk about it afterwards. Yes, but the computer vision people, they will use networks to represent the volume and do differentiable rendering, and basically then just like do auto differentiation with PyTorch, and they tell you, oh, you don't need to do this sort of stuff that is basically manual and difficult. Yes, everything's automatic. But,
yeah, it is. They are powerful, and they are quite a bit of competition compared to physics-based models. But in my work, we hope, at least if we know the physics, we try to our best to model the physics and understand how the system works. But yeah, if it's difficult to model, we try to turn to these methods.
okay, we need to just go to the next talk. If you have questions, please ask after the break. Please join me to thank speaker again.
Thank you very much.